In this video, we shall look at a few review problems on Kepler's third law. First, a brief introduction. Let's assume you have two bodies, say a star and a planet. Assume the planet goes around the star in a circular orbit with radius r. Now let's assume the mass of the star is capital M and the mass of the planet is little m. We know since this planet is moving in a circular orbit, there is a centripetal force acting on that planet directed towards the Sun, and the expression is given as follows. The mass of the planet, the speed or the tangential speed of the planet squared, over the distance from the Sun. Now we label the tangential speed in that manner, that's your v, and the centripetal force on the planet is directed towards the center of that circular orbit, namely the Sun. We have also reasoned in our previous video that this centripetal force is provided by the attractive force between Sun and the planet given by Newton's law of gravitation, which is the universal gravitational constant times the mass of the planet times the mass of the Sun over the square of that distance between them. So you see the mass of the planet cancels out, and we can write the tangential speed in terms of its angular speed, namely like that. And we know the angular speed is related to the period of the orbit in a following manner, 2 pi over the period. So substituting this in here and substituting the expression for v in here, we get r squared omega squared, which is 4 pi squared over t squared, so that's your v squared, divide by r equals g, the mass of the Sun, over r squared. So this r will cancel one of the r from the top. And let's write down the expression for t in terms of r. So it's t squared equals 4 pi squared over g times the mass of the Sun times the cube of the center to center distance between the planet and the Sun. And this is what we call Kepler's third law, that states the square of the period is proportional to the cube of the orbital distance of that planet around the Sun. Now let's look at the applications of this expression. Problem 1. A geosynchronous satellite has the same orbital period as that of the Earth. At what distance from the center of the Earth does this geosynchronous satellite orbits the Earth? And also find the orbital speed of the satellite. So that's the Earth, and the satellite is right there at some distance r, which is what we want to determine. And it has some speed, which is the orbital speed, which is also something that we like to determine. Note, Kepler's third law form is given by the following expression: 4 pi squared over g times the mass of the Earth in this case times the cube of that orbital distance. The mass of the Earth is given as 5.98 times 10 to the power 24 kg. And since the orbital period is the same as that of the Earth, the period is quite simply 24 hours. So let's put all this information inside this equation and solve for the r. T is 24 hours, so turning that into seconds, you have to multiply 3600 to it. Don't forget to square, the square that comes with the period, equals 4 pi squared over g is 6.67 times 10 to the power minus 11 times the mass of the Earth is 5.98 times 10 to the power 24 r cube. And we can solve for r. Solving for r, we get 4.23 times 10 to the power 7 meter. And that's part A. Now let's calculate the orbital speed of the satellite. Now orbital speed is given by the distance it travels, which is the circumference of that circular orbit, 2 pi times the radius of the orbit, divide by the period or the time it takes to complete one orbit. We know what r is. We have computed that in part A, 4.23 times 10 to the power 7 meters. The period is 24 hours, so again changing that into seconds by multiplying that with 3600, and you get this orbital speed in meter per second, and the answer is 3076 meter per second, and that solves the problem. Problem 2. A certain binary star system, binary means you have a couple of stars, star 1 and star 2, each with the same mass of 2 times 10 to the power 30 kg, revolve about their center of mass. So the center of mass is that dot right there. The distance between them is 1.5 times 10 to the power 11 meters. So that is the value of r, the center to center distance between the two stars. Find the period of revolution in years. So these two stars should have the same period. So let's concentrate on just one of them and see what the free body diagram tells us. Since both are revolving about the center of mass, we know that, for example, if you take the right-hand side star, it would have a centripetal force towards the center, or towards the center of mass of the system. The centripetal force is given by the mass of the star times the distance from the center, in this case it's r over 2, times the square of its angular speed. And we know this is provided by the attractive force between the two stars. And that expression is given by Newton's law of gravitation, which is universal gravitational constant g, the product of the two masses, over the square of the separation distance, r squared. So 1m from the left-hand side will cancel that m from the right-hand side. Also keep in mind the angular speed can be expressed in terms of period as 2 pi over period. So let's substitute this in here and solve for the period. You will get r over 2. Omega squared is 4 pi squared over t squared equals g mass over r squared. And we get the following for t squared, which is r cubed over 2 4 pi squared over gm. Note the appearance of 2 in the denominator for this expression that was absent in our standard treatment a few minutes ago. The reason for this is that in this problem the two bodies are orbiting about the center of mass, and the distance between either of these bodies to the center of mass is r over 2 and not r. Now let's substitute the numbers for the mass and also the distance to find the period of revolution. You get t squared equals r is 1.5 times 10 to the power 11, don't forget cube, over 2, 4 pi squared, over g is 6.67 times 10 to the power minus 11, and the mass is 2 times 10 to the power 30 kg. This 2 will cancel the 2 from the top, giving it 2 pi squared, and solving for t, you get 22,347,237 seconds. Note that you want the answer in years. In 1 year, there are 365 days, and in each day there are 24 times 3600 seconds. So by taking this number and dividing that by this, you'll get your answer in years. So that means T in years is 22,347,237 divide by 365 times 24 times 3,600 years. And that will be 0.709 years. And that solves the problem. Problem 3. Two stars of mass 4 times 10 to the power 24 kg, so that is this and that, revolves in the same circular orbit of a radius 6 times 10 to the power 9 meters around a central star of mass 2 times 10 to the power 25 kg as shown below. The orbiting stars are always at opposite ends of a diameter of the orbit, as you can see represented by this white line. So what that means is, at a later time, one of the stars is here, the other star will be there, namely at the opposite end of the diameter of the orbit. What is the period of revolution of the stars? Let's concentrate on one of the two stars, let's say the top one here. Of course, it is being attracted towards the center. Now that means it has a certain amount of centripetal force acting on it, and that is given by mr omega squared, and omega squared is 2 pi over its orbital period squared. This centripetal force is provided by gravitational attraction from the central star and the gravitational attraction from the other star at the opposite end. So let's write these two attractions. So the first contribution is from the central star, and it's given by G, the product of the two masses, little m times capital M, over the square of the separation distance, which is r squared. Now comes the other contribution due to that one. It is G, the mass of this and this are the same, so it's m squared. The distance between them is 2r, so square of that is 4r squared. This m will cancel that m. So let's bring this r to the other side, and you will get 4 pi squared over t squared equals g over r cubed m plus little m over 4. What that means is, solving for t, you will get 2 pi r to the power 3 over 2 over square root g times capital M plus little m over 4. Substituting the numbers, you get t being 2 pi, your r is 6 times 10 to the power 9 meter. Don't forget the power 3 over 2. Over square root, g is 6.67 times 10 to the power minus 11. Central mass is 2 times 10 to the power 25 kg, plus the little mass is 4 times 10 to the power 24 kg over 4. The unit of seconds, so that's going to give you 78,025,072 seconds. In years, it is 2.47 years. And that solves the problem. Thank you for watching.